Hello everyone, for this tutorial video, I'd like to explain optimization problems, where the specific feature you want to optimize, i.e. maximize or minimize, is not related to the other features by a simple equation. For example, if we are told that two poles are 20 meters apart, and one is 6 meters tall and the other is 15, and that a length of wire is attached to each tip of the pole, that goes diagonally toward the ground, like this, and asked to figure out where the wire should be staked exactly to get the maximum angle, we would see that unfortunately, the angle is not nicely related to the lengths, so we will have to use some creativity and foresight to solve this problem. In particular, we can specify the base lengths of the triangles formed by the poles and wires, as well as the angles of these triangles right next to the angle between the triangles. We see, because we have 20 feet specifically between each pole, one base must have a length of x, and the other base must have the remaining length, or 20 minus x. And we see the angles of the two triangles plus the angle between them forms a straight line, and we know a straight line measures 180 degrees. So the angles will add up to 180. So now we can get all of the degrees in terms of an x, using trigonometry. In particular, tangent of left degree equals 6 divided by x. Tangent of right degree equals 15 divided by 20 minus x. So we specify these degrees are the inverse tangents of what we found. And see, the degree in between the two degrees must be pi minus these 2 degrees. Since we have a formula for the degree in terms of x's, we take the derivative. The derivative of the first term as a constant is 0, and the derivative of the other two functions are composite functions, where g of x is the inside argument to the inverse tangent, and f of x is the inverse tangent itself. So we use this fact, as well as the difference of derivatives rule, to compute the derivative of this. We simplify it algebraically, and seeing by the quadratic formula that x has 2 critical points. But in our case here, the first one is not in the interval specified, so we discard it. In conclusion, we only have one possible critical point for this situation. In conclusion, when x equals this critical point, we have maximized our angle. A problem similar to this is, if we are given a piece of sheet metal 60 feet wide, and we want to fold 20 centimeters of these up on either end, and we want to determine the angle that will maximize the volume of water in the trowel. We do this by first using geometry to split the trowel into a right triangle, and a rectangle. And we use rules of trigonometry on the right triangles, like in the last example. In particular, we see, since the trowel has the same cross-sectional area throughout, its volume will be maximum when its cross-sectional area is maximum. So the cross-sectional area is the areas of these individual pieces. The area of the triangles in terms of trig is base equals 20 the hypotenuse times cosine of theta. Height equals 20, also the hypotenuse, times sine of theta. And we know a rectangle is simply base times height, or length times width. We see we are given the rectangle has a length of 20, and we see the height of the rectangle matches exactly the height of either triangle. So now we have a formula for the entire area in terms of an angle. We can factor out 400 from this, take the derivative using the constant rule, the basic trig functions, and the product rule for the right hand side. Simplify by expressing sine squared as 1 minus cosine squared. Seeing because we are subtracting negative cosine, this adds up. So we have 2 cosine in the formula now. And lastly, we can factor it to get it easily in terms of critical points. We see the cosine must either equal negative 1 or 1/2. So in turn, the degree must either be pi third or pi. However, if we exceed pi half, from looking at the diagram of the trowel, then the trowel will no longer be in the proper shape. So we discard pi as a possible answer. Similarly, we do not tack on a plus or minus 2 pi times n, by similar reasoning that it would exceed the limits of the angle that keep the trough in its proper shape. So now, we test the minimum and maximum angles as well as the angle at this critical point. So we see from plugging in the numbers that the critical point gives us the maximum cross-sectional area and hence volume. Now that we have figured out more sophisticated optimization problems with relation to one variable, we are ready to tackle problems involving related rates of change instead of only one rate of change as we've been looking at so far. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.